looking at what is this system, what are the constituents of the system, I would like to take another crack at explaining attitude. I think some of you had difficulty understanding attitude when it was first introduced. Slightly. You guys are okay? So I'll take another crack at it. Okay. Think about. So what is attitude itself? Orientation. So just like position, attitude is also relative. Okay. So you have to look at it in the context of something which is known. All right. How do I determine the attitude orientation of this duster? First, I have to define the reference, right? So the reference could be corner. It has to be it cannot be just this surface, right? Can I just define the attitude with regards to this surface? You need at least two directions. So if I take this as the orientation, so this could be the x-axis, this could be the y-axis, this could be the z-axis, right? Or z-axis. So now when I do this, with respect to what axis am I rotating this? X-axis, right? So you have about x-axis. How about y-axis? Z-axis, right? So the attitude is changing with respect to the table. So this direction is established. This direction is established. To form this basis, how many directions do you need? To form this coordinate basis, you need at least two directions. You can take this and this and this, or this and this. The other one will simply be the cross product. Okay, so you say if this is x, y, this is z. Okay, you have to always look at it from the cross product and the right hand sense. It's always x, y, and z. Okay. Now in space, you have to establish this reference first. Okay. Now how do you establish this reference in space? Sun. So keep in mind the sun direction and the magnetic field direction, let's say, is the other direction. They are not going to be perpendicular. You understand? Everybody understands that? They will not be perpendicular all the time. So how do we get this perpendicular? So what you do is, this is one direction, right? Everybody is able to see this? So this is one direction. You're able to see this? This could be the other direction. If you take the cross of this, you'll invariably get this perpendicular, which has to be perpendicular to both of these.
Again cross product.
Right? Then again do a cross product to get the third one. So you see why two directions are required? At least two directions are required. Right? So if you look at, clear? Anybody, for anybody, it's not clear? You want me to explain it again? So let's look at this vector. So I'm going to call this the sun vector in the inertial frame, right? Inertial frame. So this vector, now let's look at the direction of that corner. Okay. Does the direction of that corner, the vector, does that change? Does the corner itself change? No, but how you see it will change, right? If you look at it from standing on this table, it will be different. If you look at it from somewhere else, it will be different. The components will be different. You agree? The x, y, and z components will be different, right? So can I call this? Can I name this something like? It has a, this is, what vector is this? Sun vector. This is the direction vector, not necessarily the, when you say sun vector, it could be the position and direction. When I put a hat on top of it, it becomes the direction vector, okay? So if you see the direction of sun, there is an x component in the x direction, there's a y component in the y direction, and z component in the z direction, okay? Similarly, what is the other vector? We generally use the magnetic field vector. B is denoted for magnetic field, okay? And again, right? So these two vectors, are these two vectors perpendicular? Not necessarily, right? These will not be perpendicular. Now what we are trying to do is, keep in mind when the satellite is orbiting, let it be any orbit, let it be any point around, for example, Earth, the direction of sun is known in the ECI frame. ECI frame is Earth. For simplicity, I'll call the Earth frame, the Earth inertial frame. It's simply Earth-centered inertial. And we looked at this Earth-centered.
Geocentric.
It is the geocentric frame, yes. It's a geocentric inertial frame. The center is at the Earth center. The x direction is the, we looked at the x direction. You remember we looked at the geocentric? Huh? Yes, yes. So the x direction is in the vernal equinox. It's in the, not vernal equinox, but it is in the direction of Aries on the day of vernal equinox. X direction is pretty well defined. What is the z direction? Huh? Axis of rotation. Axis of rotation, can the axis of rotation be this or this? Huh? It has to be this, keep in mind, because Earth is rotating like this. Do your hand like this. If you figure out in which direction Earth is rotating, this has to be the axis of rotation. This is not the axis of rotation because Earth is not rotating like this. You see that? So this has to be the north direction or the axis of rotation. Okay. So in that reference frame, this is known. If you take that reference frame and put it wherever the satellite is at a given instance of time, this direction is known. Okay, there's a model, there's a sun model. If you just have that sun model on your satellite, this vector will be known. Okay, you have to, how are you going to get the position? GPS, right? So you just use a GPS, and if you just input the GPS position of your satellite, the model, the mathematical model will give you the x component, y component, and z component of the sun vector. Similarly, it will give you the x component, y component, and z component of the magnetic field vector. Now you take these two, you assign Rs to be equal to let's say I, okay, I direction, RS crossed with RB is equal to J, and I crossed with J is equal to K. So what you have done is, you have looked at this vector, you have looked at I and J are perpendicular,
Yes, sir.
J and K are perpendicular,
Yes, sir.
I, J, K is the orthonormal basis. What is an orthonormal basis? The three vectors are orthogonal and they are
Perpendicular.
orthogonal means what? Perpendicular, and they are normalized. They are unit vectors. So orthogonal basis means they are not unitized. Orthonormal basis means vectors are perpendicular plus their magnitude is 1. Okay, so this is an orthonormal basis. We have established a orthonormal basis just based on the vector information, the direction vector information. So this is very critical that you divide this by the magnitude. Even if it is just a unit vector, when you take the cross product, you have to still divide it by the magnitude to get this as a unit vector. So you see, I, J, K now is a basis. Right? So what we have established is, we have established this direction, and this direction. Knowing probably the sun direction is in this. Magnetic field is somewhere here. If we take the cross product, we are going to get this direction. If we take cross, we are going to get this direction. Okay. Now, so what vector is, again, in what basis is this vector defined? What is the reference frame here? X, Y, Z, or the Earth-centered inertial, right? This is the geocentric or X, Y, Z is the ECI frame. It's called the ECI. ECI stands for Earth-centered inertial. This sun vector at that point in the orbit, at that position in the orbit, this is the sun vector. Depending on the position of the orbiting body, does the sun direction change?
Yes.
Yes.
Obviously, right? If your satellite is moving, let's say that corner is the sun, if the satellite is orbiting, that direction is changing, right? So given a position, that sun direction is established in the Earth-centered inertial frame. Alright? So using the sun's direction and the magnetic field direction, what you do is you establish this orthonormal basis, IJK. Got it? That is in the reference basis. Now, the same vector as seen by the SC is spacecraft or the satellite, as seen by the satellite. Is it the same?
No, sir.
It's different, right? So what you're going to do is, you're going to do this R, S, X, okay? And I'm going to use the small x. plus R sy small y plus R sz So you understand the difference between this vector and this vector?
Yes.
You understand the difference?
That is from the earth, center of the earth as the origin. This is from the satellite.
Right. So what you're doing is the frame which is attached to Earth, you're moving that frame to the position of the Earth. You get it? The Earth-centered frame is there, right? This ECI frame is there. You're taking that frame and you're moving that frame to where the satellite is at that position. So that in that frame, okay, but the satellite itself will have its own frame, right? So if you look at this frame, this is a frame, okay, reference frame. If I take this frame and wherever the satellite is, I'm moving it. The frame is not changing. But if you look at the satellite, what is the satellite frame? The satellite frame could be X, Y, and Z, right? So depending on how the satellite is rotating, that frame is changing. So this vector, as seen by the satellite, is changing. You see that? Everybody sees that? So now what we are trying to do is, we are trying to establish this rotation with respect to these two directions. You understand? Somewhat?
The satellite, when orbiting, it's also rotating.
Yes. It will do that. It will have angular motion about some axis of the satellite. It's probably doing this when it comes out of the deployer. It will have some angular motion, and the frame attached to it is also having that angular motion.
Okay, then when we use the actuators
Mhm.
or torques,
Mhm. That is when it will stabilize. Yes. So that is when it is.
No, even during stabilization also, the satellite will keep on moving.
Yes. Even when you stabilize, it will keep on orbiting.
but once it sets the orbit,
Mhm.
then it will not be changing its frame.
The frame will change.
Even satellite will be rotating, the axis will be go on exchanging. Only axis around which it is rotating will not change. The other two axes will be changing.
The reference frame will not change. Okay, when it is rotating, the reference frame. When I'm talking about the Earth-centered inertial reference frame, this will not change. This will move with the satellite. It will not change.
That's okay.
Yes.
I'm asking, you told, na, satellite frame itself, that will change.
Yes.
That means that if the satellite will rotate.
Yes. Yes. So if you look at Earth is, look at Earth and Sun. Okay, this frame will be heliocentric inertial frame. Got it? The Sun, there's a frame at the center of the Sun which is not rotating, but the frame which is attached to Earth itself will keep on rotating. Right? You understand? So the frame, better? Slightly better?
Yeah, I thought about how the orbiting of the satellite.
Uh-huh.
But once we give this stabilize, okay, orbit is being stabilized.
Not orbit. The angular orbit is, you cannot really control the orbit as such. It is fixed.
Yeah,
But
once
the-
it is launched, it is fixed.
Yes.
But orientation,
Orientation. So, for example, if your camera is mounted here and your satellite is orbiting like this, you want your satellite to do this, right? So it will be doing this, okay?
let's say it is doing this, and it is also at the same time orbiting. The first thing you want to do is stabilize it in whatever direction you want it. You stabilize it, then do a control maneuver to point it like this, and it will keep on pointing in that direction. You have to maintain that.
Still, it will be changing.
If you don't maintain it, it will change.
Yeah. Again, I want to correct it
Yes.
often.
Yes. So it's like driving on a. If you leave, you can control it, right? A car, but you cannot leave it saying it will be in that direction. It will still. A little bit of disturbance will get it to make it tumble. So the control action has to be there persistently. So you have to switch on the wheels, you have to switch on the torquers every so often to stabilize it. Clear? Any questions? I want you to understand this. This is very important. See, attitude is very important for any subsystem. Understanding attitude is just a little bit challenging, but we have to make an attempt to understand that. Okay, so is this clear? This is clear. Now you understand why the sun's direction is changing as looking from the satellite. Let's say you're sitting in that satellite. Okay, is the sun's direction changing?
Yes, sir.
How much is it changing? How do we know in what direction is it changing?
With respect to Earth.
With respect to Earth, yes. So with respect to Earth, is the sun's direction changing?
Yes.
At a particular position, it is not changing, right? If you look at the particular position, it is there itself always. Okay. So if you think about, that is the reason position is very important when determining the attitude. So the first thing is you input a position, and then this vector will be at that position. You understand? That is known to us. We have very well mapped the direction of sun anywhere around Earth. We have very well mapped the direction of thousands of stars around Earth. Anywhere, you put us anywhere around Earth up to moon, we know where the stars are. We have a very detailed map of 5,000-10,000 stars. Okay, so the map will tell us this direction is this star, this direction is this constellation. We very well know that. Okay, but when the satellite is changing, we have to have a system on board the satellite to determine, looking from the satellite, where are those stars. So that is what we use. These. How do we get this vector?
Locating the Earth center,
Spacecraft.
where other stars.
Think about this. We have discussed this. How do we get this vector?
Other stars.
We are looking at the sun's direction from the satellite. How do we get the sun's direction from the satellite?
Sun sensor.
Sun sensor. You see that? This we get from the
Sun sensor.
sun sensor. This we get from the model, mathematical model. You input position, the mathematical model will throw out this vector. This is gotten from sun sensor. You see how this can be gotten from sun sensor? You have 6 sun sensors on 6 faces, right? Regardless of what the satellite is doing, 3 of them will be, at least 1 will be facing, at max 3. Can more than 3 face sun? It is impossible. Mathematically, that is impossible, right? So the 3 vectors are these. The normalized components are these. You see it? Similarly, you get the What is XYZ? Small XYZ is satellite frame. Right, exactly. Okay, so once we do this, we can take this RS. How do we get this?
Magnetometer.
Magnetometer. So the sensors give you the direction of either celestial objects or the magnetic field direction in the satellite or the spacecraft frame. You get it? You get these two, what these two information they are giving you, they are telling you the direction, the same direction. One is sun vector, the other is magnetic field vector. But one is gotten from the mathematical model based on the position, the other is gotten from the onboard sensors. So these are required for figuring out the, now you take these exact, so these two directions are the same, right? These two, this direction and these directions are the same. This is pointing to sun, this is pointing to sun. This is pointing to magnetic field, this is pointing to magnetic field. Okay, now if you do this, if you say RS spacecraft is equal to small I, okay, and RS crossed with RB is divided by RS crossed with RB is equal to J. And keep in mind, I am always using this hat, which means it is ortho. We are constructing a orthonormal. These are all unit vectors, orthonormal basis. Okay, and then I crossed with J is equal to small k. Again, divide by. Don't ever forget to. Okay. Now, what is IJK? IJK is another basis. Okay. Now, if you compare this base and this base, you get the relative attitude of the spacecraft. Does that make sense? If you compare this base, so what you're going to do is you're going to express so you have I J K is equal to, remember this, we did this last time? You recall that, right? So here what happens is, so I'm showing you rotation about one of the primary axes. What are the primary axes? The XYZ are the primary axis. But it is not going to do that all the time. The rotation can be about any axis, right? So if you're, let's say if I ask you to go to, from that corner, if I ask you to come to the middle, what are you going to do? Are you going to do, I'll take X, Y, Z. You don't do that, right? You just go there, right? So the rotation can happen, any rotation can be expressed as a rotation about one axis. Any rotation. But to better understand, we look at it from basic rotation. Just we look at it as X, Y and Z. We look at, for any random rotation, it can be so much about X, so much about Y, so much about Z. You see that? Hello? Something there. The phone, is it? The phone, yeah. It will be fine. Huh? All right. So here, so you're going to get this. Get a matrix here. Okay, and then you have I, J, K. This matrix is the relative attitude of spacecraft with respect to ECI. Does this make sense? Slightly? I'm not expecting you to know completely or understand completely, but a little bit idea of what spacecraft attitude is, right? So now once you know the attitude, or once you know the orientation, and if I tell you what the angular rate is, angular rate of that particular object, can you figure out how the attitude is changing?
Yes.
You can do that, right? So this is attitude determination, okay? So all this I talked about, you'll do something like that. So you have a model for this. This is the sun model, all right? This is the magnetic model. There's a magnetic model. It's called there used to be WMM. Look up WMM. WMM stands for World Magnetic Model. And then now there is IGRF. It's International Georeference, something like that. So just look up that. So those models will give you, your satellite will have those models on it. Okay, it will just be a mathematical model and it will be on one of the systems. Okay, that model, if you give the position in terms of latitude, longitude, that model will output the vectors. You got it? These are gotten from the sensors, right? Now, if you know this, determining this matrix is attitude determination. Okay, this matrix is called the, what is it called? It's called DCM. DCM stands for direction cosine matrix, or it is also called transformation matrix. It's sometimes called rotation matrix. Okay, this is the determination, attitude determination. Attitude determination is the process of determining this matrix. Okay. Do you guys have any of you used quaternions? You know what quaternions are? Mathematical constructs? No? You know matrices, right? So quaternions, nobody has used quaternions. Okay. So let's not discuss. So you have attitude determination. The process of determining this matrix is called the attitude determination. Now you use angular rates which are given by omega, you can do attitude propagation. How do you propagate position? How do you propagate position? How do you propagate position? Come on, it's not that difficult. How do you determine position? GPS. How do you propagate position? Incremental. How do you keep on adding position? Cars, how do cars propagate position? How does the odometer work? Or the speedometer work? Huh? How does speedometer work? Right, so what is in that rotation, this thing? What are those called? So that rotation, something is measuring that rotation, right? Those are called? No, differential is different. Encoders, motor encoders. You've heard about motor encoders. So if you have encoders, encoders will give you the angular displacement. And if you how do you convert angular displacement to linear displacement?
Into
Huh?
Omega is equal to
2 pi.
2 pi m into r.
R theta. No, not R theta.
2 pi into
2 pi into angle. How do you convert angular displacement into linear displacement? Huh? Theta is what? Angular displacement. R theta is linear displacement. The sector length is R theta. What is the sector length for an entire circle? 2 pi. So if you're looking at 2 pi is one complete circulation. R is radius. So 2 pi R is circumference. R theta is part of the circumference. Okay. So R theta is the way to do it. R theta will give you that displacement, right? And theta is, so your encoders will not give you 2 pi at a time. Theta, it will give you small thetas. And if you multiply that by R, you're going to get the linear displacement. Now if you have the position in GPS, can you add those values and keep on propagating the position? You see that? How else do you propagate position? What are used for propagating position? Huh? Yes, somebody said, I heard that. Accelerometer, yes. Accelerometers are used for propagating position. How do you use accelerometers? Accelerometers will give you acceleration in the x and y direction. So whatever direction you're going, you get the acceleration. If you integrate acceleration, velocity. If you integrate velocity, displacement. So if you keep adding that displacement to the absolute position, you're going to propagate position. You see that? So similar to accelerometers propagating position, you use gyros. What do gyros give you? Angular rates. Gyros will give you angular rates. If you integrate angular rates, angular displacement, or simply angle. Okay, it will just give you angle or angular displacement. And if you add this angles, whatever direction you get it, to this attitude, you can propagate the orientation. Whatever absolute orientation you get, you keep on adding the angular rate. You can propagate the attitude. Okay. Now what you are going to do is, the team has been identified, right, for ADCS. In my opinion, again this is subjective, and maybe because I am biased to this, I enjoy this so much. This is the most interesting design of the satellite. But again, it's my opinion. There are faculty from telecommunication. They may feel telecommunication is the most interesting. The faculty from electrical engineering, they may feel otherwise. But this is just because there are some of the coolest people who lived on Earth worked on this, like Newton, Euler, Kepler. So those were the cool dudes. So now what you need to do, even if you look at not just them, the moon mission, anything we sent to space wouldn't have been possible if somebody hadn't figured out all of these. For example, the Apollo mission, where astronauts were sent to the moon, there were people diligently working out this math. Okay, and they had to figure out, because if you're off by even a little bit, so how do you go from, you know how you go from Earth to moon? You just don't go there. You don't just do that, okay? Huh? You spiral, okay? You cannot just walk there. You know? You cannot just, let's go straight. Let's take the shorter distance. You cannot do that. Right? You have to spiral, right? You have to do that. If you have Earth here, if you have moon here, you start like this, right? And then you do this. You do this. Okay, and then you do this, and then suddenly you go burn your hand and do this. So to figuring out where exactly these burns have to happen is an extremely challenging thing to do. If you're off by even a little bit, what happens? Just say goodbye. Right? So you have to imagine, if you're off, why is attitude important when you're doing translational motion? When you fire the thrusters, right, the direction in which the satellite is oriented has to be pretty accurate. If you're off by a little bit, right, and you fire the thrusters, have you tried to, let me think about this, have you used those dart boards? How many times did you get the bullseye? No one, he already knows. Nobody hasn't. So you imagine what is important is how you hold it, right? And so thrust, you are applying that thrust. Now if you cannot hit a bullseye, imagine this. This has to be as accurate or even more accurate than the bullseye. So you have, your satellite has to be oriented such that if it fires, it has to go and hit the bullseye. So it has to hit the bullseye. So these attitude calculations are very critical. You can do communication, you can do, sun is really big, right? So you can, even if you are off by a little bit, do you think the solar cells will not get charged, or the batteries will not get charged? They'll still get charged. Communication, if you're off, if I talk here, you guys can hear? Yes. Yeah, you can hear because but even if I do this, you can hear me, right? If I do this, you still can hear me, because sound travels in a omnidirectional way, right? So it travels in like a spear, right? It goes everywhere. Now you cannot do that with the thrust. The thrust has to be in the very accurate direction. Okay? So that is the reason this is as important as it is. So you want to take a break and come back?
Yes. I should see 15 there. The right time.